we've got the position of a particle given as a vector 4t cubed comma y of 2t, where y is a twice differentiable function. And we want to know the acceleration vector at t equals a half. So all we need to do is take a couple of derivatives, right? So what should our velocity vector be? Derivative of 4t cubed should be 12t squared. And what's the derivative of y of 2t? That should be 2 times y prime of 2t. Yeah? Everybody good with that? And what should our acceleration vector be? Our acceleration should be 24t. And then the derivative of 2y prime of 2t should be 4y double prime of 2t. And if we evaluate those each at a half, what do we get? Should get 12 comma 4y double prime of 1. Good or no? Any questions or issues with that? All right. This one should be exceptionally easy. We're already given a velocity vector. So if we're given a velocity vector to get to the acceleration vector, it should just be a derivative. Our acceleration vector ought to be 2t comma 5. And if we evaluate that at t equals 3, we should get 6 comma 5. Easy, yeah? They like to put these ones into the multiple choice. These ones were, all these acceleration vector ones were actually multiple choice questions. I just didn't put up the multiple choice options. Once again, we're given a position vector, t cubed minus t, comma 2t minus 1 cubed. This is our position. So our velocity should be 3t squared minus 1. And this should be 3 times 2t minus 1 squared times 2. And then our acceleration vector should be 6t, comma, and this would be, we'll have we have 6 times 2t minus 1 squared, so that'll become 12 times 2t minus 1 times the 2, or 24 times 2t minus 1. Everybody good with that? And then we'll evaluate it at 1 to get 6, comma 24. Easy enough? All right. And last one of these that we're going to do before we move into the polar question. If we're given a position again, we're looking for the acceleration. Like I said, they love these ones. So velocity vector should be 2t, and then a natural log of 2t plus 3 ought to be 1 over 2t plus 3 times 2. And our acceleration vector ought to be 2. And then the derivative of this ought to be negative 4 over 2t plus 3 squared if you use the reciprocal rule on that. And we didn't have to evaluate that one. Easy enough? All right, so now I'd like you guys to take a couple of minutes and look at this one. So I'll give you, how about, I don't know, 10 minutes. I think 10 minutes ought to be plenty to do parts A, B, and C here for this polar curve. And they give it to you in Cartesian form, and then later on they have you do stuff in polar form. So about 10 minutes to work on this. If you guys all finish early, let me know, and we can start looking at it before that. Ready to go. So for the first part, that should be pretty straightforward, just showing that the derivative is equal to negative 4x over 3 times y plus 1. So we'll just take the derivative of this implicitly. So that'd be 8x plus 6y dy dx plus 6 dy dx equals 0. And if we subtract over the 8x, we got negative 8x, and then divided by 6y plus 6. And we can divide those both by 2 to get negative 4x, and we can factor out the 3. That part should have been pretty straightforward. Any issues with that? Hopefully not. All right, so for the next one, part B, we just need to find the second derivative. So dy dx is negative 4x over 3 times y plus 1. The second derivative we could find by taking the derivative of this, implicitly 3 times y plus 1 times the derivative of negative 4x, which is negative 4, minus negative 4x times the derivative of 3 times y plus 1, which is just 3. And then all over 9 times y plus 1 squared. Everybody good with that? And if we wanted to simplify that a little bit, we could. They both have a 3, so we can cancel out the 3's and turn this 9 into a 3. Oh, did I forget my dy dx? Oops, sorry. That's on, yeah, 3 dy dx. Sorry. Kind of forgot the most important part, huh? All right, so we can cancel out the 3's first of all. And then our dy dx will plug back in. And so we've got negative 4 times y plus 1, and then a minus a negative 4x becomes just a plus 4x times our negative 4x over 3 times y plus 1, all over 3 times y plus 1 squared. And that answer is good enough. If you want to get a common denominator here of 3 times y plus 1 for this, you can, and then drop that down here and make it a 9 times a y plus 1 cubed. That's fine, but you don't have to do that. If you chose to do that, you'd end up with a negative 12 times a y plus 1 squared minus 16x squared all over 9 times y plus 1 to the third. Good or no? All right, so then what about part C? So part C, we got to think a little bit about what it's asking us here. It says that the curve is given by this 3 over 2 plus sine theta for 0 to 2 pi, and wants us to find dr d theta. So we haven't really found dr d theta. How do we find dr d theta? It's just the same as this is r equals something in terms of theta, so that's just like finding a dy dx if we have y equals something in terms of x, or a dA d theta if we have something a equals something in terms of theta. So we're just really differentiating 3 over 2 plus sine theta. So dr d theta yes, Adrian, just take the derivative. Yeah, I just saw that in the chat. But, so dr d theta, and what was r? R was 3 over, go back and look at it. It was 3 over 2 plus sine theta, yeah, okay. So dr d theta, then we can just use the reciprocal rule on that. So it should be negative, and then 3 times the derivative of sine theta, so negative 3 cosine theta, over 2 plus sine theta squared. And what's the question asking us? It's asking us, as theta increases, on what intervals is the distance between the origin and the point r theta increasing? Okay. So what does dr d theta represent? Well, dr means a change in the r value with respect to theta. And so the distance between them is increasing whenever dr d theta is positive. So we want to know, when is this greater than 0? That's our question. And so we know that the denominator of this is always positive. So really what we need to figure out is, when is negative 3 cosine theta greater than 0? Or effectively, when is cosine of theta less than 0? And when is cosine of theta less than 0? Which quadrants? Should be in the second and the third quadrants. So theta is less than 3 pi over 2, greater than pi over 2. And because this is we're talking about when is this increasing, or increasing, decreasing functions, they still are on these theta ones. Still going to want you to put a closed interval on that. Good or no? You're saying use a sine chart, find the values where theta is equal to 0 and 2 plus sine theta is equal to 0, and then put them onto a sine chart like that. Now you don't need to do that. You could if you wanted to, but this is good enough. Yeah, we know that we're just looking for when it's greater than 0, when dr d theta is greater than 0. So if you can solve that equation pretty easily, then that's fine. Or solve that inequality. Any other questions on that? All right. So you guys told me you didn't want to do much more practice AP stuff yet, that you want to get through optimization and related rates and the other applications of the derivative that we're going to talk about. So we'll do that in the next couple of days. It'll probably take into Monday. Should be able to do optimization today, no problem. And then related rates in a bit on Monday. I mean, on Sunday, whatever day it is, tomorrow, Friday, and then a little bit more on Monday with some other stuff. So we'll start with optimization. I always like to start out by reminding you of the things that you need to do for optimization problems when we're looking for a max or a min of something. So make sure you read the question until you understand what's going on. Usually drawing a picture is going to help you out. On occasion, that might not be necessary. You're gonna have to write your own equations. And number 4, where you graph and figure out the domain, you don't necessarily need to graph it if you don't want to. In fact, I probably usually won't, but it's good to know what the domain of your function is so you don't pick a value for your answer that's not within the domain. and then figure out how to maximize or minimize whatever you're looking for and do it. And then always prove that your thing is a max or a min by either using a sine chart or by using the second derivative test. You should all be familiar with optimization problems, at least to a degree. So let's do one. We want to find the point on the graph of y equals x squared plus 1 that is closest to the point 3, 1. So we will read that question over and over again until we understand what it's asking. Hopefully we already understand what it's asking. Here's the graph of y equals x squared plus 1. And here is the point 3, 1. So we're curious, somewhere along here, there is a point that is closest to 3, 1, somewhere along this parabola. And so we're trying to figure out exactly which point along this parabola that is. Everybody good conceptually with what we're supposed to be doing here? Okay, so if we're looking for a distance, what formula do you think we should use? We're looking for the point that makes this distance a minimum, right? We want to use a distance formula. And we're looking for the point that makes this distance a minimum. So the function that we need to have needs to represent distance so that we can take its derivative and find the minimum value of that function. So we'll use a distance formula for the distance between any 2 points. Should be this, we'll call the distance z. So z should be equal to the square root of what? y2 minus y1 squared. What's y1? That's this point, right? 3, 1. So something minus 1 squared. What's the other y value that I'm looking at? What is this y value? Right, it's our function, right? X squared plus 1. So we got x squared plus 1 minus 1 squared, and then plus the other one should be x minus 3 squared. Everybody good with that? So this becomes the square root of x to the 4th, right? X squared plus 1 minus 1 squared is x to the 4th, plus x squared minus 6x plus 9. Everybody good with that? And we want to figure out when this is at a minimum, so we'll take the derivative. Figure out when it has horizontal tangent lines. So dz dx, our derivative should be 1 over 2 root x to the 4th plus x squared minus 6x plus 9 times the derivative of that, which is 4x cubed plus 2x minus 6. Good or no? Hopefully. Okay. So first off, any values that make this undefined are not in the domain of z. And we should be able to see that because anything that makes the denominator here 0 would be an x value that makes root x to the 4th plus x squared minus 6x plus 9 equal to 0. And if that means that the distance would be 0, and clearly the distance between this point 3, 1, which is not on the parabola, and any other point on the parabola can't be 0, right? So we know that this distance is always going to be greater than 0, and therefore any undefined values on it don't make any sense in the context of our problem. And so all we really need to look at is when 4x cubed plus 2x minus 6 equals 0. And if we wanted to, we can make that 2x cubed plus x minus 3 equals 0. And how are we going to solve that cubic? We'll have to use, we can't factor by grouping, we'll have to use the rational root theorem. What are the possible rational roots of this function? Plus or minus 1 and plus or minus 3 divided by plus or minus 1 and plus or minus 2. The factors of 3 divided by the factors of 2. And what do you guys want to try? Try 1, -1, a half, -a half, 3, -3, or 3 halves, or -3 halves. Sure, 1 seems like a good choice. So if we try 1 with our synthetic division, 2 for 2x cubed, 0 for 0x squared, 1 for 1x, and -3 for our constant, and do synthetic division, drop down to 2. 2 times 1 gives us 2, 0 plus 2 is 2, 2 times 1 is 2, 1 plus 2 is 3, 3 times 1 is 3, and add those and get 0. And we can see that that worked out really nicely. So x minus 1 is a factor of this, as is 2x squared plus 2x plus 3. First off, we know that this gives us x equals 1, right? And then this one, 2x squared plus 2x plus 3. If we just look at the discriminant of that, right? If we just look at b squared minus 4ac, we'll see that that's 4 minus 24, which is less than 0. And if the discriminant of a quadratic is negative, it means it has no real solutions. So the only value that we have here that is possibly a minimum is at x equals 1. And we can test that in 2 different ways, and I'll show both ways. One way is by taking a second derivative, so z double prime. Z double prime would have been 12x squared plus 2. And if we plug 1 into that, we get a value that is z double prime of 1 is greater than 0, which tells us that this is a min. Or we could have done it with the sine chart, plugging in something less than 1. Like, for example, if we plugged in a half to this, we'd have a half minus 1, which is negative, and then this is a positive plus a positive plus a positive, so that'd be positive, so negative times positive. And put in a number larger than 1, like 1,000, that's positive and positive, and we'd see again that it's a min. And so I believe the original question asked, find the point on the graph. And so we know that it's at x equals 1, and so y of 1 should be 1 squared plus 1, or 2. So the point that is closest is the point 1, call it 2. Okay, so Molly, you're right. I shouldn't just use that. I shouldn't just use the denominator. I mean, sorry, I shouldn't just use the numerator. But the, well, no. So, you know, I'll answer both of those sort of together. The denominator is not, I mean, the denominator is always positive, yes, in dz dx. But the question Molly's asking is with the second derivative. I didn't actually use this full first derivative, and part of the reason for that is I know that this piece here, if I'm trying to minimize or maximize something that's inside of a square root, the square root doesn't affect it in any way, actually. So I could have just used this function if I'd wanted to, and so that's one reason that I didn't have to use this denominator and didn't actually have to take the full derivative. I actually, as I was going through though, I just sort of forgot that I had a denominator to it. So that's my fault. If we'd done that though, so let's see, if we think about what would happen to this, if we take the derivative of just this whole thing, we're going to end up with a positive times this other positive once I take the derivative of it, and then minus a positive, or actually minus 0. This ends up being 0, right, at x equals 1. So that whole second part of it, that minus part disappears. So we'd have a positive times a positive minus 0, and then over this squared, which is still going to be positive. So it'll still end up being positive. So we should have done that. That's my fault. We should have had 2 root all this stuff times 12x squared plus 2 over 2 root all this stuff squared for our second derivative. And then, yeah, the root and the root here and the 2 and the 2 here will cancel, and I'm still left with 12x squared plus 2 over that same denominator. And that same denominator is still always positive. So it wouldn't have affected it, but you're right. I should have not said this was z double prime. Right? That's not actually z double prime. That was me just forgetting that I had a denominator. So you're right. Everybody good with that? But do keep in mind that if you want to, at this point, you can say something like minimizing or maximizing a square root of a function. The square root doesn't matter because the square root is at a minimum when that function is at a minimum, and the square root is at a maximum when that function is at a maximum. So you could make that statement and then just use x to the 4th plus x squared minus 6x plus 9 as your function. Is that good for everybody or no? You guys still alive out there? Oh, good. One of you is still alive. 1 out of 22. Not bad. You're not alive, Luke. I'm impressed that you could type while not being alive. Very skillful. Are we ready to start the next one, or are you guys still sitting and thinking about that one? All right, so let's take a look at this next one. We got a rectangle. We're going to inscribe that rectangle under one arch of the sine curve. And so if we talk about inscribing something under a curve, it means it's going to go, it's going to touch the curve with a couple of its vertices if possible, and then also go along the x-axis. And we want to know what's the largest area that rectangle could have and what the dimensions are that give that area. So first we'll draw a picture. Our picture is going to be one arch of the sine curve. So there's one arch of the sine curve. And we're going to throw a rectangle into there, and I'll just use the x-axis as my bottom piece of the rectangle. And we want to know what's the largest area that that rectangle can have. Well, the area of a rectangle should be the length times the width, or the base times the height, or whatever you want to call it. Call it length times width. True. So we need to figure out what is this length and what is this height, this width. So first off, the width should be the easy part. What's the width? How high up does this go? Yeah, it goes up sine x, right? But it only goes up sine x as long as this distance here is x, right? We have to call this distance x to have gone up sine x. Everybody agree with that? Okay. And if that distance is x, a sine curve is symmetric, right? And a rectangle is symmetric. And so the distance from here to here should be the same as the distance from here to here, which means that this gap that I have between the curve and the rectangle and this gap that I have between the curve and the rectangle should be the same, right? This should also be x. And exactly, Adrian, the length, since we know that this is a sine curve, one x-intercept to the next x-intercept is pi units long. So the length ought to be pi minus 2x. Everybody good with that? So our area function is pi minus 2x times sine x. And we're looking for what x value will maximize that area, right? So we need to find a prime. We need to take our derivative. That would be a product rule. So pi minus 2x times cosine x plus, we'll make it minus because this is going to become a minus, right? When I take the derivative of pi minus 2x, we'll get minus 2 sine x, right? And first off, is this thing ever undefined? Nope. So then we just need to set it equal to 0 and see what x value makes that 0. And we should be able to use our graphing calculator to figure that out. Should all have a graphing calculator, right? So what do we have? We had what was our equation? Pi minus 2x times cosine x, and then minus 2 sine x. Right. So pi minus 2x. No, that didn't work. Pi minus 2x times cosine x minus 2 sine x. And just to make sure we remember how to do this, we want to be able to figure out the x-intercept of that, and we do that second. Calculate 0, choose a value to the left of the x-intercept and hit enter. Choose a value to the right of the x-intercept and hit enter. Hit enter again, and we end up with 0.7104627. Everybody good with that? Is that what you guys got? So that's the x value at which we are potentially at a min or a max. We'll need to do a sine chart with that to show if it's a min or a max. So we'll put that as 0.710467. And we're looking at the graph of the derivative. And to the left of that, the derivative is positive, and to the right of that, the derivative is negative. So positive to negative means increasing to decreasing, which means that it's a local max. And if we've got a local max there, we can now just go back in and answer the question, what's the largest area? Well, the largest area should be pi minus 2 times 0.710467 times the sine of 0.710467. And what'd you get for those? You can round to 3 decimals now. What'd you end up with? .652. Okay. Everybody good with that or no? And if we wanted to know the dimensions, we just plug it in separately. We figure out what this first piece was and this second piece was, but I don't think we need to do that necessarily right now. Good? Any questions, any issues? Everyone feeling okay about basic optimization stuff here? All right, let's do another one. You got a different answer? Oh. Multiple people got a different answer? You gotta stop trusting people to do their calculator work and all that correctly. 1.122. All right. Don't worry, Nick, I'll never trust you again. So Molly, I only picked one. I should have said this, but I only picked one because this next one over here, if I'd found this next one, we'd see that this is, well, I mean, this one's a min. Clearly that one's a min, right? Going from negative to positive. But I believe, let's see, what is the value there? 2 point something, we'll just call it, it's not quite 2.5, but we'll just call it 2.5, right? And if you think about the domain for our function, right, well, x has to be less than half of pi, right? Because x can't be more than halfway over here. And so half of pi would be, 1.55-ish, right? And so we couldn't have a value that's more than that. We couldn't have a value that's greater than 2 as our x value. Does that make sense? Yeah. So that's the part where I didn't explicitly write it out, but where I said, think about the domain of your function. Well, your domain of your function here is that x has to be greater than 0, but less than pi over 2. All right, everybody good? All right. So we are going to construct an open-topped box. We're going to take a metal sheet and cut the corners off of it into congruent squares and fold them up so that we get an open-topped box. So we're starting with something like this that is 20 inches by 25 inches. And we're going to cut off congruent squares from the corner. So far, good? Okay, and if we're going to cut off congruent squares here, we'll call each of those like x by x, right? And so what is the volume of this box? All right, so we should have 20 minus 2x and 25 minus 2x. And then the height should just be x as we fold it up. Exactly. So x times 20 minus 2x times 25 minus 2x. And if you want to, I don't know, if you want to distribute that all together just so we can use the power rule, then that's fine. What do we end up with if we just distribute that all together? 20 minus 2x times 25 minus 2x is going to give us what? Constant of 500 times the x will be 500x, and then a minus 90x squared, and a plus 4x cubed. Everybody good with that? And what's the, so I'll try and be a little bit more clear about our domains now. What do our x values need to be between? X got to be greater than 0, right? Because we got to cut something off. But x has to be less than what? Has to be less than 10, right? Because we can't cut off more than 10 inches. In fact, we can't cut off 10 inches because if I cut off a 10-inch square, well, I'm not going to be able to make a box out of it, right? Because the shorter sides will be gone completely. Everybody good with that? I hope. So what do we get for v prime? Yes, Adrian. 2 times 10 is 20. That's excellent arithmetic. That was very good. So what's our v prime? (500 minus 180x plus 12x squared). And we want to know when does that equal 0? And it should never be undefined, right? Because it's polynomial. So when does 12x squared minus 180x plus 500 equal 0? Well, it might be easier if we just simplify a bit first. Perhaps. You can at least divide them all by 2, right? We divide them all by, we can divide them all by 4. I think 3x squared minus 45x plus 125 equals 0. And I don't know, does that factor nicely or no? No? All right, well, then we'll end up with x equals 45 plus or minus the square root of, all right, what's 45 squared minus 12 times 125? Anybody know what 45 squared is off the top of their head? Should be what? 16, 18, 2025? Is that right? The whole thing comes out to be 5 root 21. Alice? You guys want to trust her on that? Anybody want to check that? Or no? Are you positive, Alice? Because last time Somebody said something that was wrong. All right, we're going to trust you. Which one is the actual value that we want to use? Is it the 45 plus or the 45 minus? Have to use the minus, right? Because 45 plus 5 root 21 divided by 6. I haven't done that on my calculator just to confirm that that's more than 10, but I'm positive that 45 plus 5 root 21 divided by 6 is definitely more than 10, right? So we'll use 45 minus 5 root 21 over 6. And we want to show that that's a max. And so we can either use a sine chart or we can use the second derivative test. In this case, it's probably just as easy to do either one. We'll just do them both real quick. So what's V double prime equal? If V prime was this, we should have negative 180 plus 24x. I know, Molly, that's not. Oh, that is our original. I was thinking I was taking the simplified one, but I didn't even take the simplified one. So that's actually what it is. I was going to make sure with that we hadn't taken the simplified version. So we plug in that value that we've got there. 45 minus 5 root 21 over 6. Anybody have an approximation for that, just so we can evaluate? Alice, you got an approximation for that? 3.681. Great. So 3.6811869. And if we plug that in here, we can clearly see that if we evaluate that at x equals 3.6811869, that's going to be less than 0, which is going to tell us that it's a max. That's good enough. Or we could have done the sine chart. And we would have found that it was positive here and negative here. And then it was max using V prime for our sine chart. Everybody good or no? The idea of optimization coming back to you hopefully after 4 months of not doing it. For those of you that successfully took the AP test the first time last year. We know that's not you, Adrian. Didn't you have to take the AP test like 3 times last year because your computer kept crashing on you? Or something, your internet went down, or like, have you actually gotten a score back yet? Oh, good. All right. I was afraid maybe you were like still on the 12th retake or something. I just hadn't heard from you. All right, should we do one more? I won't ask what your score was in front of everybody else, since by the time you took it, it was already like 2025 or something, probably. So we want to design a 2-liter or 2,000 cubic centimeter can that's in the shape of a right circular cylinder. And we want to know what dimensions will use the least amount of material. So the amount of material that's used, if we're neglecting the thickness of it, should be a surface area. So we'll call this a surface area equation that we're looking for, that we want to minimize. So the surface area should be what? For a cylinder. What's the surface area for a cylinder? should be 2 times pi r squared, that'd be the top and the bottom, right? Plus the lateral surface area. And the lateral surface area should be 2 pi r, which is the circumference of the base times the height. So 2 pi r squared plus 2 pi r h. Everybody good with that or no? Elon, Darius, you guys good with that? All right. So now the problem here is that we've got an r and we've got an h in here. And so we need to figure out a way to eliminate one of those variables. And we are given some other information that the volume should be 2,000 cubic centimeters. And what's the volume of the cylinder? It should be the area of the base times the height, right? So we could replace height with 2,000 over pi r squared. So our new area function will be 2 pi r squared plus 2 pi r times 2,000 over pi r squared, which should simplify to 2 pi r squared plus 4,000. Pi's cancel, and r over r squared should be r to the -1. Everybody good with that being our final equation for area, or surface area, in terms of just r? Okay, and a prime then should be 4 pi r minus 4,000 r to the -2. And if we want to see when that's equal to 0 and when that's undefined, we want to get a common denominator and put the fractions together. So put an r squared down here and make this into an r cubed. And so we know that this is undefined if r equals 0, but having a radius of 0 doesn't make any sense, right? We can't have a radius of 0 to have a cylinder. And so we'll check when this equals 0. So that'll be when 4 pi r cubed minus 4,000 equals 0. Or when pi r cubed equals 1,000, or when r equals 10 over the cube root of pi. Good or no? Okay, and then once again, 2 options, either a sine chart or a second derivative test. Doesn't really matter which one you use. Let's do just the sine chart this time. So here's 10 over cube root of pi. What is that about? Anybody got an approximation for that? Thank you, Alice. 6.827840633. Wonderful. So something more than that would be 9. Plug in 9 into our derivative. The denominator of r squared is going to be positive, right? And then the numerator, 4 pi times 9 cubed. So I think 9 cubed, we know, is 729 times about 12 is going to be, looks like a negative value, right? I'm sorry, a positive value. And plug in something like 1 that's less than that. Denominator is still going to be positive, and the numerator is going to be a negative, right? 4 pi minus 4,000 is definitely negative. And so we can see that it's a minimum. And so the dimensions would be a radius of 10 over the cube root of pi, and we can find our height, because height is equal to 2,000 over, what was it, 2,000 over pi r squared, right? And we could we could simplify that if we wanted to. Pi over the cube root of pi squared is just a cube root of pi down here in the denominator. And 2,000 divided by 100 should just be a 20 up there. And I don't know, we had centimeters, I think, right? The height of 20 over the cube root of pi and a radius of 10 over the cube root of pi centimeters. Everyone good there or no? All right.